All right, thank you for having me. So my name is Dillon Gardner, and today I want to talk to you about why I think AUC is worthless and some of the lessons that I've learned in making a transition from academia to working in business and data science. And so to start, I want to talk a little bit about my background because these are my biases, this is where I come from. I'm going to share a lot of opinions with you. Some of mine you might think are incorrect, so this is where I'm coming from. So my background is in physics. I have a PhD in experimental physics from MIT. I've been working as a data scientist for 7 years, and I've worked in a number of different fields. I've worked in electricity markets, programmatic advertising, ag tech, fintech, and I've worked in companies as small as 4 people and upwards of about 800 people. I've held roles sort of as an individual contributor and also as a manager, and I think one of the most important things for this talk is I've also had the experience of being laid off. And I think that's a very rude and harsh awakening to some of the realities of doing work in business. And it's definitely informed a lot about how I think about these things. So to motivate this, I want to have a little bit of a preamble and talk about job descriptions. And so if you look at a job posting such as this one, this is from Enigma, which is a really great company. It happens to be the company that I currently work at. And we're hiring, so if you're interested, take a look. Here's a segment of the job description. And what you'll see is there's a number of, I don't know if not exactly requirements, but things that you were looking for that I would say lean very technical. And then in addition, there's some other requirements. This one I'll highlight that is somehow something other than the real technical skills. And so here we're talking about, we're looking for people who approach data as an artifact of the real world and develop repeatable strategies for validating results against ground truth. And so there's something where we're really trying to emphasize the fact that this is a real world problem. This isn't sort of toy problems. Here's another job description. This is for Apollo Agriculture. It's a really great company. It's the company I used to work for. I'd highly recommend you check them out. They're also hiring. And here we have a lot of different things that are being looked for, and 2 of them that I want to highlight here are comfortable explaining complex solutions to non-data science peers across multiple continents and cultures. And the second one is having product management skills to maximize impact of data science work. So we're sort of emphasizing these communication skills and really getting the impact out of the work. And just in case you think that I'm cherry picking these examples of the companies from which I worked, here's another company. You may have heard of them. I'll let you make your own decision about whether or not it's a great company. And there are similarly these non-technical things where we're looking for experience articulating and translating business equations and using statistical techniques to arrive at an answer using available data. And the second one, which really is probably 2, but the one I want to emphasize is effective written and verbal communication skills. And then if we contrast that to the syllabus that we may have. So this is the Intro to Machine Learning course from MIT. It's the first class that I took in machine learning, and everything is purely technical. This is also true if you look at sort of data science boot camps. There tends to be a very strong technical emphasis in the syllabus. And also if you look in sort of the literature, so you're learning from books and things, there's this very strong technical emphasis and very little emphasis on these other skills that we know the company wants. And so what I'd say is there's a little bit of a mismatch here. And what companies want is in part driven by the fact that there are many people and different people are looking for different things. So you have a data scientist who's involved with the hiring process, and they might be looking for what we can say are these are the sort of standard 3 pillars of data science, where we're talking about machine learning and programming, statistics and math, and domain expertise. But on top of that, there's also sort of a business persona. There's business people involved, and they're looking for things that are slightly different. So they are really emphasizing the nature of real-world data. We're not working with toy problems, but something that's fundamentally rooted in reality. A strong emphasis on communication. And here, it's not like the ability to give a really nice talk at a friend's wedding. It's about how do you communicate across the business of how can you make sense of the data science work that you're doing. And the third thing is a little bit more like product management, which is saying, how do you really take what you've done as a data scientist, and how do we get value out of our hard data science work? And so, to me, I think there's a mismatch here. When we talk about what we think of, and by we, I mean all of us as data scientists, what we think leads to success is maybe something like this, where it's like an 80-20 mix of these technical skills with other skills. And in reality, I think what leads to success is more like 50-50. And so this mismatch is something that I've really noticed in my career, and something that I want to try and help us as data scientists get better at understanding this and what successful might look like. I think it's also helpful to sort of think about why is there this mismatch. And so these are my opinions from thinking about this, and I think one of the major reasons is that classes, programs about data science, about machine learning, tend to be taught by academics. And as an academic, you have another job, and that other job is doing research that is looking to try and expand what is possible in data science and in machine learning. So typically, somebody who's teaching a data science class might also be spending their time working on doing something like improving the error rate in ImageNet, which is a way that we're using to say, here's a new technique, and this technique is moving our field forward. But that looks really different from what happens in a business setting. I also think that we are just, as general, as data scientists, we are more comfortable with assessing technical skills. And so when it comes time to doing job interviews, we typically will build a panel around the technical side, because that's something we're comfortable with as data scientists. I also think we're more comfortable teaching technical skills. And so the way in which we tend to think about how can we improve as data scientists, there's this strong emphasis on technical because our mentors are comfortable. If you are working as a mentor, if I'm working as a mentor, it's easier for me to focus on the technical. And then the fourth reason is I think that as data scientists, sometimes we disdain some of the business side. So this one, okay, I will admit I'm maybe not quite as certain about, but I think this can be a pattern that can happen. So with this in mind, I want to do a little bit of a trip to business school. And the way I want to do that is I want to start talking about scoring functions. When we do our work as data scientists, it's really helpful to make a clear distinction between loss functions and scoring functions. When I talk about loss functions, what we're talking about is what the ML algorithm is trying to minimize. The scoring function is more in line with what the business is trying to minimize. So you might also think about this as a cost function or a utility function, in which case maybe you're maximizing it. So a loss function will need to have really nice mathematical properties. Maybe it needs to be differentiable. These are the kinds of things that you're ultimately doing gradient descent, you're doing backprop on in order to minimize. And a scoring function can be very, very arbitrary. So as examples, if we think about loss versus scoring functions, in our loss function, we might have something like the root mean squared error. We might be talking about cross entropy. We're thinking about things like regularization. And in our scoring functions, we're thinking about things like accuracy, F1 score, AUC. Okay, so these loss functions, when we're doing this as data scientists, what happens is there's these two different kind of processes that happen. For the loss function, this is where the internals of our algorithm is trying to do the optimization, and we're trying to do some kind of gradient descent type of optimization. Whereas when we're doing the scoring functions, what we're talking about is the model selections. This is like hyperparameter tuning. We're doing things like grid search in order to figure out which of all of these candidate models that we can build are going to do the best according to the scoring functions we care about. And in reality, though, it's not just a single scoring function. There's more complex way we can think about it in terms of businesses. And so for a business, they don't really care about accuracy, F1 score, or AUC, except as a proxy for the things that they really care about, which are things like profit, your loss ratio, maybe things like your model complexity, explainability. I've worked in the past in an organization where we were heavily regulated, and so we needed to work with regulators to convince them that this model was actually going to work. And so in that case, we needed to be very explicit and penalize ourselves if we were using a complex model, because that was harder to get through the regulatory environment that we were operating in. And so there's this sense of business optimization as well. And the thing that I would argue, though, is that we're better off if we're working in business as data scientists to not think about these academic scoring functions, but instead, when we're doing our model selection, we should be thinking about these business scoring functions as well. And so we want to, as early as possible, start taking these kinds of considerations into account when we're doing our work as data scientists. Okay, so if we think about like how products are discussed if we're working as data scientists, an often thing that happens is something like this, where there's a business person who's thinking about profit, loss ratio, model complexity, explainability, and the data scientist is talking about accuracy, F1 score, and AUC. And when you're in this situation, this is a recipe for failure, okay? This is the kind of thing that'll lead you to getting laid off, or your team laid off, or your business will fail. So an alternative thing might look like this, where now the business people are talking about things like accuracy, F1 score, and AUC. And when you're in this case, like this works. Like this can be successful, and this can lead to praise, promotion, pay raises, all the great things that we want when we're working in a company. But the thing that happens here is most of that's going to go to the business person, because they are the people who did all of the work to try and take that business consideration and then map it into something that we can use our tools for as data scientists. So a better way to do this is if, as a data scientist, you and your team and our team start using the languages of business. And this will also be successful. And in this case, the preferential praises, promotions, pay raises will go to us as data scientists, because we're doing all of that hard work to figure out how can we map our clever data science work into the things that the business cares about. Okay, so how do we get there? And so I want to spend a little bit of an aside talking about ROC curves and AUC just to make sure we're all on the same page. And so an ROC curve, the way we think about this is it's a trade-off between the false positive rates and the true positive rates. And so the true positive rate is the fraction of positives that we're correctly classifying as positive. And the false positive rate is the fraction of negatives that we are classifying as positive. And in these diagrams, we say this diagonal is just random. So if we're just have a random number generator, your model will live on this diagram, on the diagonal of this diagram. And if we're better than random, we're going to live in the top left. If we're worse than random, we'll live on the bottom right. But in reality, you can't be worse than random because you just multiply by -1, and then you're better than random. So a model might live on your diagram and it looks something like this. And what this is expressing is the way in which your model has gotten to the point where we can have different trade-offs between true positives and false positives. And if we start with 100% rejection, so we're saying we're calling everything false, then we start down in this bottom left, and we end up, if we move all the way to accepting everybody, we end up in the top right, and the model is the trace of the curve of what's possible. Or the model line, yeah. And the AUC then is just the area in this squiggle, and so this will go from 0.5 if you have a completely random model, and 1 if you have a perfect model. Okay, so now I want to talk through an example of how this would look in practice. And so the example I want to talk about is loan applications. So business people come up and they say, hey, give me a model that determines if an applicant for a loan should be approved or should be denied. And then we as data scientists say, great, I'll build a classifier that learns to predict who will repay a loan. And yeah, so for this, we'll make the simplifying assumption that everything is paid either as a lump sum, so it's 100% repayment, or you don't pay at all and it's 100% default. Just make things easy for us. Okay, so now we go off, we do our work, and we're like, all right, we have success, we have a model. This is wonderful. But how do we know that this model is any good? And how do we know that even if it is good, if it's better than the cost that it takes to use this model? And how do we know that this model is better than no model at all? So how do we answer these kinds of questions, I think, is the critical part. And then if we have two models, now I have two different choices, which of these models are better? If you're thinking about something like AUC, then you're like, well, obviously the model with higher AUC. But this is really an unuseful way of thinking about it if you're working in a business environment. What we really care about is which trade-off between the true positive rates and the false positive rates will give us better options as a business. So to motivate how we're going to make that decision, we'll start by thinking about our confusion matrix. And what I want to do is go through and figure out what is the value in each of these squares of our confusion matrix. That is to say, what is the business going to gain or lose for each of these 4 possible outcomes? And that's literally what we need to do. Like, we need to fill these things in. And so how do we go about doing this? Well, it's not necessarily your job by yourself. It's not our jobs as data scientists to know these answers. We need to go talk to the business and figure this out. So we need to go talk to the CFO, talk to the CEO, talk to the product manager, and try and figure these sorts of things out. In the case of this loan example, you could say, well, look, if somebody applies for a loan, our model says they should get a loan, what happens? Well, we get the price that we're going to charge them, but we also have to add in the cost of the goods and services that we're giving them. We have to add in the interest that we need to pay during that time period. And we have to add in the cost that we paid to acquire this customer. So these would be things like your marketing costs. It would also include like application costs for them to go through your process, including your model. What happens, on the other hand, if our model says that this person is a good credit risk, we should give them a loan, and they don't repay? We have all of the same costs of goods and services, interest, and the customer acquisition costs, but we don't get the price that we're charging. They didn't repay. In the case that our model says no, then the impact on the business is actually the same. It's just the customer acquisition cost. It doesn't matter whether they would have repaid or they wouldn't have repaid, and in fact, we probably won't ever even know which would have been the case. Okay, so then you say, wait, is this right? And I think this is an important point, is that, like, it's maybe, like, we don't really know for sure. Some of these things might change, things like your marketing costs, customer acquisition costs. Like, we don't really know. And there are other terms that you might consider adding in. And so in the past, for example, I was working for a company that was involved with this, and we realized that we had an additional value that we wanted to account for, in that we preferentially wanted to give out loans because that's how our models got better over time. If we didn't give out the loan, we don't get the data back in order to figure out how do we improve. So we wanted to add in some kind of explicit representation of that, which we had as like a value of learning. So there's some uncertainty here. And in the end, you might end up with like filling these numbers in, and it might look something like this. These numbers are made up. They are just completely random because they made the rest of the examples look a little easier. All right, and now what we want to try and do is take advantage of these numbers, and then we can calculate the utility for each point in this true positive, false positive space to help us understand which of these different trade-offs are better. And so this is where I would say, okay, now we're going to do our little algebra crank and try and calculate the expected utility in this true positive, false positive space. And to do this, we'll start by saying, okay, we need to define these terms. We'll say the prevalence is the probability that a given example is positive, which we'll say is the total number of positive cases in our example divided by the total number of cases. And the negavance, which is something that I just made up right now, is the probability that an example is negative. So it's 1 minus the prevalence. And if we take that, then we can explicitly write down the expected utility for any one applicant for any point in this true positive, false positive space. And okay, this is how it works. If you don't believe my algebra, happy to talk to you about it afterwards. And that's now where we are. So now we have this idea of how we can figure out in this space where everything is. And so to start with, we can say, look, like, what happens if we just reject everybody? And so if we plug that through, and we're operating in a situation where the prevalence is 0.5, which is to say half the people repay, half of them do not, then each applicant that we're rejecting is worth minus 10, which is to say we're paying minus 10 in the customer acquisition cost for everybody who applies, and then we just reject them. So probably not a very good business model. And then we can say, okay, well, what happens if we accept everybody? And so if we accept everybody, we can look in this formula, plug in these numbers, and we end up at minus 26 units. So an even worse business model. And so if you're in this situation, your default choice, if you don't have a model, is just to reject everybody. Obviously, we want to do better than that. Okay, so let's go back to our little algebra crank, and one of the things that we can do is for a given amount of utility, if we keep that as a constant, we can see that in this true positive, false positive space, for a constant value of utility, there's this linear relationship. And so we can solve for this, and we can say that the slope is independent of the utility, and the intercept matters on the utility, independent of the expected utility, only the intercept matters on the expected utility. Okay, so now here what we can do is we can draw a line, and so this is the same utility as rejecting everybody. What this line means is I can be completely indifferent anywhere on this line, and I will have the exact same result in terms of the impact on the business as if I just rejected everybody. This is all the same. So that's the point, okay? So this is the first major thing, and I think this is like maybe a little bit counterintuitive. Anywhere on this line is worth exactly the same. Similarly, we can say, okay, what happens if we were accepting everybody? Everybody, everywhere on this line is going to be worth exactly the same as rejecting everybody. And we'll see that in general, we can write a series of lines on here with increasing utility as we move up and to the left. So each one of these lines, as a business, we are completely indifferent where we live on, but we want to be climbing up this slope to higher and higher utility, which goes up and to the left. Okay, now if I say that like there are good macroeconomic things happening, and so people are more likely to repay their loan, the economy is doing better, and so the prevalence goes up to 0.6 from 0.5. So nothing changed in our business, just everything is external to us. Suddenly that means our slope changes. And the thing that is really important to notice is once this happens, the best option by default becomes accept everybody. And so this change in slope matters a lot. And it all happens relative to 0. So in this case, the slope is now less than 1, and whenever that happens, that means your default choice should be to accept everybody. Okay, so the slope is the thing that really matters. And so this is what I'm saying with the slope changes. So on the left, the slope is less than 1, where our default choice is to accept everybody. On the right, it's greater than 1, so our default choice is to reject everybody. And that means that when we're doing our model, this helps us understand ahead of time where we're going to get the most value out of our model. In the first case, when we're in the top left, we can have a model with a very small AUC, but we can still get value out of it as a business. In the other case, we really want to be on the bottom, here, and we can still get value. So it can still be a small AUC, but we're going to start doing a lot better than our default choice as a business. Okay, so then how does this work if we are if we have a model? And so once we have a model, now we're doing a constrained optimization problem. And so this is the problem of, you can think of this as Lagrange multipliers, and what happens is the optimal point with a model is going to be at the tangent of these lines. And so this is a property of Lagrange multipliers, and the way we can intuitively think about this is we're trying to climb up as high as we can get, but we have to live on this curve. And that highest point that we can possibly get to on a curve is when we start walking completely parallel to the slope. And so that's where the optimal point is going to be once we have a model. Okay, so the optimal choice is going to either be on a tangent line of our model, or it will be that our model ends up not being very valuable, and it will be either 100% reject or 100% deny. The other thing that's interesting about thinking about this math is that it tells us already something that I think a lot of people intuitively think about when they're dealing with an ROC curve to think about their model, is that they often think about their threshold is typically going to be in an area where there's a lot of curvature to your ROC curve. And this is the mathematical underpinning of why that's the case. It's saying that there are many, many different slopes in an area of high curvature that are likely to be the optimal point. So even if you're slightly wrong in terms of estimating the utility matrix, you're still probably going to want to live in this area of high curvature. Okay, so I want to show you a different case. This is now if the slopes change because the prevalence changes, now a model with the same, oh, that's not what I did, sorry. If I flip my model, and now my model is the same AUC, but in the other side of the space, this model doesn't do anything for us because we're still always below the curve that is the same as rejecting everybody. So even though this model has the exact same AUC as the previous model, it doesn't help us. We're still better off as a business to just reject everyone, which, you know, kind of unfortunate. Okay, so what I've sort of seen here then is that it's really the slope is the thing that matters the most when we do this math. And so as a physicist, one of the things that I always learned is, you know, you look at an equation like this, and we try and sort of look at extremes of what happens. How do we try and make sense of this? And so when we look at this, like one of the things to think about then is, you know, what happens when the slope gets really, really big? That happens when it means we need a high precision model, meaning that it's going to be hard to beat, just reject everybody. And so I can look at this slope and say, what are the things that would make this true? And so that's going to say, if, for example, the cost of a false positive goes really, really high, then that means that we're probably just going to be in a position where our default choice will be reject everybody. And so we can get value by having this very high precision model with maybe a very low acceptance rate. Conversely, when the slope is very small, that means we need to have a high recall model. It's going to be hard to beat just accept everybody. And so that would be, for example, if like the true positive is very, very high, then that's going to change where we need to be focusing. The other thing that's really interesting to point out is that all of these terms come in pairs and they're subtracted. And that means that if there's any term that we think about the utility of this that shows up in every single term in our matrix, then it's not going to impact our slope at all. And that means that it won't impact our optimal decision. So this is actually the mathematical representation of like the sunk cost fallacy, which is to say, you know, once you've already paid that money, it doesn't really matter. You shouldn't make any decisions after the fact. So if we look in the way in which we were defining this before, you'll see that this customer acquisition cost shows up in every term. And so what that means is when we're making a decision for how we want to set our thresholds, then we actually don't need to consider customer acquisition cost. And the reason for that is because you've already paid that. That money's already been spent as a business by the time that application gets to the data science model, so it doesn't matter. So this is something that maybe you already know. You know, you remember your high school economics. I certainly forgot it. You run through this problem, and then you sort of see the value of doing this kind of effort to know that you're making these decisions intelligently. Okay, so summary. When we talk about the utility in ROC curves, what happens is you get the curves of constant utility are going to be straight lines. The slope is the thing that determines the behavior in the absence of the model. And also the slope determines what region of the ROC space we want to try and live in as modelers. The optimal points are typically going to be tangents, and so that's why we need to be focusing on the areas of large curvature. And then, if the model results are bad, this can happen. Even though you have, you know, real ability in your model, there's a positive AUC, then it still isn't working. And so maybe you need to change the business. So maybe you need to think about reducing your customer acquisition cost, think about changing your price, things along these lines. One of the things that you know, I always think about too when dealing with a model is it's really helpful to figure out when does this break down. So this is a toy model that I made, and it doesn't capture everything. It's very helpful, but it doesn't capture everything. So here are some of the ways it can break down. One thing that this doesn't include is any sort of feedback loops. So in reality, if you start changing your acceptance rate as a business, then you're going to change who's going to be applying. And so there's that kind of feedback loop that can happen. The other thing that you can do is you can have multiple thresholds. So you don't necessarily have to just have like accept or deny. You can also have a reject, accept, or have like a human review in the middle. You could also have variable loan terms depending on the risk. So you don't necessarily have to just have a constant price, but you can change the price. Also, this is modeled as like an unending stream of applicants, where you just are saying accept or deny on an unending stream, and in reality, you might have capital constraints. So instead of just trying to optimize on a per applicant, you need to consider how much money can I possibly lend out as a business. And then the other thing is it's not always super simple to figure out what the business is trying to optimize. And so this is sort of a per customer optimization, but you might be thinking about things like lifetime customer value, things like this. And sometimes it's so hard that if you're talking to the business side and people can't give you a straight answer, then maybe there's also a bigger problem with the business. Okay, so these are my conclusions and recommendations. So I'd say, it's really helpful to try and get a little bit of an understanding of the business logic. I think a lot of the ways in which the business is thought through is basically algebra, whereas all of the machine learning, these data science skills are essentially calculus. And so I'd say that if we can learn how to do backprop, we can learn SVM, then we can take the time to learn a little bit of business. It's really not that complicated. I would also say that we should do the effort to try and learn these business outcomes early. Doing it earlier as part of our model development will lead to better outcomes in the end. And finally, what I say is that as data scientists, we need to be really talking with people on the business side of the company. We are not responsible for doing all of these things by ourselves. We don't work in a vacuum. We need to be very collaborative. And we also need to make sure that when we build a model like this, people are on board that this is the correct way to think about the business. Okay. So that's my opinion on AUC. So if there are any questions, comments, or disagreements, happy to hear them.
Thank you very much. Here we go then.
Hi, thanks for the talk. My question was maybe more towards the beginning of your talk, when you were talking about, how we kind of data scientists become data scientists and how they are recruited. So what would you advise on the more like on the interviewing side of the equation, given that in order to assess someone's business skills, it's sometimes quite hard to actually set the context within a very time-constrained like interview, I guess, setting. It's much easier to assess technical skills than.
Yeah, it's a really good question. So one of the things that we do in my current company that I think is very helpful is we actually have product be involved in the interview process with data scientists. And so we've built together like a case study that is more business-centric to try and get a sense of how does somebody think about this. I also think one of the other aspects of it that I think a lot of companies do this, I've seen this in companies I've worked for, is there's also the sense on the technical skills that you really only need to kind of test technical skills to the point of capabilities, because it's often easier to teach the gaps that somebody might have. So as long as you can sort of convince yourselves that somebody has sufficient ability to learn those technical skills that they might be missing, it's easier for us as data scientists to teach those skills up and instead prioritize trying to find people who have interest, abilities, backgrounds, whatever, in some of these other skills as well.
Thanks for the talk. I really appreciate it, and yeah, especially the interaction on business aspects is very important. I agree, especially as you climb up the ladders and you're less cushioned by others. Yeah, so my only question is quite technical. So your focus here was on true positive rates and false positive rates. My understanding, correct me if I'm incorrect, but I think that graph is useful if you're dealing with a balanced set in which you're expecting a 50-50 split, and otherwise one wants to focus on precision versus recall. I remember an article like nailing that point. So what's your opinion about that?
Yeah, so actually, maybe talk through this slightly too quickly, but this is kind of what happens here. Like the difference between these two graphs is a change. The unit economics are the same, but the split between positives and negative changes. So on the right, if I remember the numbers correctly, this is 50-50 on the right, and on the left it's 60-40, and that's what changed the slopes, because that does show up in the slope equation here. So this is the term, these like RN, RP are related to the prevalence. Of course the total falls out. So this is the same thing as the total number of negatives divided by the total number of positives. So it shows up in the slope. And that's exactly the intuition that I think you can build, as you're sort of saying, is if you are in a very imbalanced way, then in some sense, if you're extremely imbalanced, then the unit economics matter less than the imbalance. And so, as long as your terms are sort of roughly the same order of magnitude, but your balance is orders of magnitude difference, then that dominates your slope term, and that will do exactly as I was sort of saying and trying to explain in this summary slide here, where it's saying like, yeah, I think this is the point you're making, right? When the slope's really, really small, you need to have a high recall model. When the slope's really, really big, you need to have a high precision model.
Okay. Yeah, that sounds about right. So you're giving like a utility function as opposed to the F1 score that all of us use on precision recall.
Exactly. And so like here, this is the point. I mean, you know, a high precision model is the model that's living in this bottom left, and a high recall model is one that's living in the top right.
Okay. Thank you.
Hi, thanks for the talk. The slopes or the utility, you said if you have a dynamic pricing that you could implement, how does it affect the slopes? Would they curve?
Yeah, I haven't really thought through that math, so
Okay.
I'm not 100% sure. I've thought through it a little bit more. If you're saying, you know, you're going to have 2 points and then, you know, human review in the middle.
Okay.
But in principle, you can do it. I mean, I don't think it's like, okay, maybe it starts getting a little more complex. But I think, you know, I don't think it changes the principle of the value of
the principle not,
exercise,
but I think
Yeah.
the slopes should curve.
I agree. I think they probably would end up curving.
This really appeals to my economics background, but one thing I wasn't sure about, are you using these utility curves as like an example of how to build a mental model? Or would you really generate indifference curves and optimize your models against them in cross-validation?
In many cases, so I have literally done this. Now, it often ends up being that when you're thinking about different models, and what you're doing here is you're trying to say, I have a model, I need to set a threshold, where should my threshold be? And when you're doing that, this might not be the best graph to be producing. You know, I think this graph is good for building your sort of mental model, but in the end, you could just plot a graph of like, what is my utility versus my threshold? I want the high one, right? So, you know, I think there are better ways of framing it at that point. I think this is a good way of sort of building up that mental model of like, hey, what am I really trying to do here? Especially as it comes to the fact that like, you're not necessarily gonna get it exactly right, particularly like what is the prevalence, because your training data and then at inference time is different. So the world may have changed. So, you know, the economy changes. Suddenly, you know, I wager for a lot of loan giving organizations right now, that prevalence is lower now than it was a year ago. So you don't necessarily have full knowledge.
Thank you.
Thank you. Cheers. We've got a couple more minutes. Any more questions? No. I'll head over here. Let's include this side of the room. Let's do it.
Thank you. So you talked about data scientists learning the language of business to be able to communicate with business, as opposed to business learning the language of data science, although you sort of said that's possible. But then they get all the praise and we don't want that. Do you think there's value in sort of meeting halfway where we learn each other's languages and that leads to defining better metrics for the business, better sort of more precise utility? And if yes, then how do you achieve that in an organization?
Yeah, that's a really good question. So I think it probably really starts depending on the ways in which you're doing models and how closely they are to like the business outcomes. And so if you're, you know, in a large organization and you're building a model that's going to be used across many different entities in some way, it starts getting a lot harder to think about like the bottom line of this particular modeling decision, because it's shared across different use cases. So in those cases, I think, you know, okay, maybe these like F1 scores or other sorts of measures might be, you know, as close a proxy as you can come up with. I think that regardless of the language being used, one of the things that I've seen is that when you're doing the data science work, when we're actually trying to make decisions about which model is better, having the outcome that really matters for the business is really important. And so, you know, I was kind of a little fast and loose in terms of how these language works, but generally speaking, when you're having those meetings, even if it's a, you know, collaboration with the product manager, it needs to have the sense of like, what are we really trying to accomplish as a business? And so it's great if product managers also can really be in the weeds and sort of saying like, okay, I see where this is hard, trying to optimize this, especially if we're in these cases with like feedback loops and things like this. And so we're going to say, hey, look, like we're just going to use this kind of measure as a proxy because we think this is the, the best way just to deliver an MVP, and then we'll iterate on it from there. So that's a little tricky one to get it exactly right. But I think as data scientists, in terms of getting people partway there, if we do a little bit of the work to talk to business, I think that also builds up credibility if then you want to say, hey, look, this is no longer the easiest way to think about it, like we need to move into a different direction.
Thank you very much. Thank you, Dillon. And I think we need to swap over for the next speakers. So if everyone could show their appreciation. Thank you very much.